Hey guys, welcome to another video of quantum field theory. In today's video, we will be talking about antiparticles. So in our videos on quantum field theory thus far, in the second part of the series, we've talked about just particles, right? We talked about how to get particles out of fields, things like that. But we haven't talked about antiparticles. But we know from experiments that there are particles that have the same properties of other particles except for the fact that their charge have a different sign. So an electron, for example, has a negative charge, but a positron, the cousin of the electron, has a positive charge. And we call the positron an antiparticle of the electron because it has all the same properties, the charge is just a different sign. So in order to actually talk about antiparticles and include them in our theory, all we have to do is just consider complex fields. The real scalar field doesn't have any antiparticles that correspond to it, but the complex scalar field does. So it's the same thing with spinor fields and vector fields. So let's actually talk about how quantum field theory talks about antiparticles. So here we have the complex scalar field. So the real scalar field had just a of k e to the minus I k mu x mu plus a conjugate k e to the I k mu x mu. That was what was inside of this for the real scalar field. And we found out that a conjugate k, it creates particles, and then a of k destroys them, right? But here, we don't have a of k and a conjugate k anymore. We have a of k and b of k for the complex scalar field. So we can carry out the same quantization procedures as before, right? We can say that a of k, a conjugate k prime, is 2 pi cubed delta of k minus k prime. And we can do the same thing for b of k. And as we'd expect, if we do the second quantization procedure, a of k would create particles, sorry, a conjugate k creates particles, and a of k will destroy particles, right? But what about b of k and b conjugate k, right? We also have a similar set of coefficients, b of k and b conjugate k. What happens? Well, b conjugate k, again, it's going to create particles, but when b conjugate k acts on the vacuum state, it won't create the same type of particle as a conjugate k, and we'll see that as we go on in this video. So basically, b conjugate k and a of k conjugate k will end up creating different particles. And we are going to elaborate on that as we move on to this video. But the basic idea here is that for complex scalar fields, we'd have A and then B, so we'd have two sets of commutation relations instead of just one, where A of k and B of k correspond to different particles. And then, of course, B of k is going to destroy this new type of particle that we still haven't discovered the properties of it yet, but we will soon. So, yeah. Now, what happens when we act on our field, our complex scalar field, on the vacuum state? If we did that, we are actually going to get 0. And why is this? Well, if we act on the field on the vacuum state, right, we're going to distribute the vacuum state inside of here. But since a of k acting on the vacuum state is 0, and b of k acting on the vacuum state is 0, we're just going to get 0. So this quantity no longer contains any physical meaningfulness. So it's not really physical anymore. So how do we resolve this problem? Well, what we could do here is we can go back to our commutation relations over here. And we can actually try, because before we had b of k, b conjugate k is 2 pi cubed delta of k minus k prime. We could instead say that b conjugate k and then b of k is 2 pi cubed delta of k minus k prime. And by changing this commutation relation over here, B of k will then become a creation operator. But it's going to be pretty unorganized. We are unorganized to kind of like define them differently for A of k and B of k. So this method isn't going to be so nice. So another way that we can get around this problem is by keeping the same commutation relations and instead writing this B of k as B conjugate k. So what are we doing when we're saying this? Well, by writing B of k as B conjugate k, essentially what we're saying is that we are taking B of k to be a conjugate of something. Because we can write any complex number as the conjugate of something. Like I is the conjugate of negative I. So you're basically just writing B of k as the conjugate of something. So that's why we were kind of still allowed to write it like that and keep our complex scalar field. So by doing this, B conjugate k is going to create particles and A of k is going to destroy particles. But they are creating and destroying different kinds of particles. But how do we know this? How do we know that they don't create the same type of particle? Well, by doing that, we can look at the charge operator. So here we have what's called the charge operator for quantum field theory. And we actually found this we found this equation from our video on the U1 symmetry. So if we employ a U1 symmetry, we get a conserved sort of quantity, that being the charge operator. If you plug in the Lagrangian for the complex scalar field, which is actually slightly different from the real scalar field Lagrangian, you would get this right over here. And we can notice that the Lagrangian for the complex scalar field, you can notice that the charge operator for the complex scalar field contains these two parts. And we can notice that this over here is just the number operator for the particles. Let's just call the particles that A conjugate k creates. Let's call them A particles. So it creates A particles. All right. And then B conjugate k is going to create B particles. So these create B particles. And it turns out that there's going to be a relation between the A particles and the B particles. So let's call this the number operator that for A particles. Let's call this over here the number operator for B particles. So what happens when Q is acting on a state that's A conjugate k acting on the vacuum? So this corresponds to one particle or one A particle with momentum k. So let's call that 1A k. So what happens when we have that? Well, we can just find that out by just multiplying this entire thing over here. We can multiply that by A conjugate k acting on the vacuum state. Now we know that's just that's the same thing as one particle, well, one A particle with momentum k, right? So we can just distribute that on the inside. Now since NA acting on this is going to give us 1 times 1AK, since N is the number operator, and then this acting on 1AK is going to give us 0. So that's telling us that we have 0 particles. Well, we have 0 B particles, right? And we can find this explicitly if we use our commutation relations, just like how we did in the video on the creation and annihilation operators. But basically, since there are no B particles in the state, when the number operator acts on the state, we're going to get 0. So as a result, we're going to have that Q acting on one A particle it's going to give us Q times that 1A particle. And also, technically speaking, the number operator contains the this integral over here, but I'm too lazy to like write it out for each one. So, yeah. So that's what we get when we act on the charge operator with the 1A particle. We find that it has a charge of positive Q. And the value of Q can be determined by experiments, basically. So what happens when our charge operator acts on 1B particle with momentum K? Well, it's the same thing as before. If we had 1B particle, this would be a B, we would distribute it on the inside, and this time Na acting on B, the B particle, is going to give us 0 since we have no A particles in the state. And then Mb acting on the B particle, it's going to give us 1 times the same state. And as a result, that's going to give us negative Q times the same state, since we have a minus sign right over there. So we have a minus sign. Let's make that clear. So that's why we have negative Q. So when the charge operator acts on the B particle, we say that it has a charge of negative Q. But when the charge operator acts on the A particle state, we find that it has a charge of positive Q. So we found out the particles and antiparticles, they differ by having a different charge. But do they differ by energy? Because remember that all the way back to when we were solving the Dirac equation, right? We found out that it has negative energy solutions. Since we do have solutions that are of this form. So say we have like some A, B while spinors, and then e to the minus imt. We found solutions that looked like this. And if you were to plug this into the Schrödinger equation, you'd get something like this, implying that the energy is negative, right? I mean, you could make the energy positive by requiring the mass to be negative, but if the mass is negative, then we have particles repelling each other because of gravity, and that's pretty weird. So Dirac made his whole C concept to sort of circumnavigate through this negative energy problem, but it wasn't really very satisfactory. So how does quantum field theory solve this problem? Well, in quantum field theory, you don't interpret this field, you don't interpret the psi as a wave function. Instead, it's a field. So this statement no longer applies in quantum field theory. Instead, we still have something like the Schrödinger equation, but it's supposed to be acting on the particle states, not the field itself. So we should have that H acting on some particle state gives us the energy times the state. And the Hamiltonian in quantum field theory looks like this for a complex scalar field. So again, if you were to run through the math, you would find out that the Hamiltonian acting on a particle, let's just call it psi A. So this is a particle state. It's going to give us E times psi A, where E is just going to be the square root of K squared plus M squared, which is just also omega. If the Hamiltonian acts on some antiparticle state, psi B, we're going to get the exact same thing because we have a plus right over here. Or in other words, A conjugate K acting on some state is going to raise the energy of the state by omega K. If this is an A state. And then A conjugate K, or not A conjugate K, B conjugate K, acting on some B state, will also raise the energy by omega K. So this is basically telling us that because of this plus instead of a minus, the antiparticles will have the same energy as the normal particles. So you don't have that conundrum anymore in quantum field theory. So yeah, that's pretty cool. Now, another question that we might want to ask is, can a particle sort of turn in to an antiparticle? Is that possible? You could use our intuition to sort of help us answer this question, but let's see what the math says of it. So I've made a little key over here because there's going to be a lot of terms that you have to kind of keep track with. So this key just tells us like the properties of each part of the field. And here what we've done is we've split our field into two parts, phi a minus plus phi b plus, where phi a minus represents this term with, of course, the integral, and phi b plus represents this term, again with the integral. So we're going to split the field into these two parts to make what follows a bit more, much more nicer. So with all of that being said, we have this over here, and we want to find the probability that a particle turns into an antiparticle. And that's going to be equal to this, right over here. But the question that you guys might be asking is, how do we know that? And the reason is that we know that phi a plus acting on the vacuum state, it creates an A particle, right? So we know that in like quantum field theory, right? To find the probability that we get an antiparticle, right? We want there to be an antiparticle in the final state. But how do we write that? Well, we can write that as phi b plus acting on the vacuum state, but conjugated because we want it to be an antiparticle in the final state. By the way, sometimes I write my conjugates as an x instead of instead of like a plus kind of thing. If you see that, sorry, but they just mean the same thing. So you want to conjugate that to get it into a final state, and this of course represents a particle, well, a B particle in this case, and that conjugate is just going to be the vacuum state times phi b, but minus this time. And so when we conjugate things, the sign of the exponential is going to change, and these pluses correspond with the sign of the exponential, by the way. So that's why this over here is a probability. So how do we actually calculate this probability? It turns out that it's actually pretty straightforward to calculate this probability. All we have to do here is we have to note something. So since this is going to create an A particle, we're going to have like 1 AT, right? And then we have this over here. Now, we could expand this out and calculate it. Let's just use our intuition here, right? This phi over here, it's phi b minus. It's going to destroy. It destroys the B particles. But since there are no B particles in this state, and it's trying to destroy B particles, we're going to get a 0 as a result. Again, we could just resort back to our expansion over here. We'd have something like B of k e to the minus I k mu x mu. And that would just be acting on this over here, which is just a conjugate k acting on the vacuum. No, not a conjugate acting on the vacuum state. It's this over here, and we kind of be multiplying this. Where did it go? We are multiplying this by that state, right? But that's just going to destroy that state because there's no B particles there. Let me think what I'm saying is sensible. Like, yeah, we're just going to have like 1AK, like some momentous state there. And it's going to destroy that momentous state, basically. But yeah, just using that sort of kind of intuition, we can deduce that this is going to be 0. So this is telling us that a particle can't transform into an antiparticle. Now we know why the math tells us this, but can we kind of draw some sort of physical meaning behind that? We know that a particle, it carries a charge of Q, and an antiparticle carries a charge of minus Q. So if a particle were to transform into an antiparticle, its charge is going to decrease by a factor of, well, -1, or kind of by a factor of 2, depending on how you look at it. So basically charge is changing signs, meaning that charge is not conserved. But since charge is conserved, that's why we can't have a particle transforming into an antiparticle. So that's sort of the physical intuition behind that. We had a mathematical intuition, but it's always nicer to have a physical intuition behind the math. So with that being said, we can also look at this right over here. Now, what is this equal to? Now we have that phi acting on the vacuum state is just this, right? So this part, let's go back. This part is just going to be phi, is it phi b? Yeah, phi b plus acting on the vacuum state. And we've deduced that this part over here, what am I looking at? Yeah, this part over here, it was equal to this, and that's equal to that. So this is equal to that. And for the same reasons that we said before, that's also going to give us 0. This is different from the free real scalar field, because for the real scalar field, what happened was that this was actually a non-zero value. This was actually our elementary propagator. But again, this is telling us that we can't have a particle changing its electric charge. So yeah, we're going to get 0. So for a lot of these amplitudes, we're getting 0, but are there any non-trivial amplitudes that we can have? The answer is yes. Now we can look at this amplitude right over here. This is an amplitude that antiparticle goes from xt to x prime t prime. And by turning throughout the math, we do find out that it is actually a non-zero. We do get this as a result. Now you guys might think that, hey, isn't this going to destroy the particle that this creates? That may seem like the case, but we technically have to expand the fields fully, and we'll find out that it's not actually the case. You can look at the same case for the amplitude that a particle goes from xt to x prime t prime. That's going to be this over here. You guys can convince yourself why that's the right expression for the amplitude. And that's going to give you this over here, which again is going to be a non-zero value. So those are the only cases where we have a non-trivial value for the propagator. If we use both phi or both phi conjugate, we would just get out a 0 value. Why did I write that? Yeah, here. Nope, I don't see where. Yeah, here. If you just use double phi, we would just get out 0 for our value. Same thing applies if you use phi conjugate, by the way. And also, there are some more sets of commutators that we should cover. There are these ones right over here. For some of the concepts that we talked about today, we'd have to use these to prove them in full detail. Basically, anything that involves a of k and b of k gives a 0. We can also write this a bit more compactly, like this, where here we have the Kronecker delta, and then here's the delta function. Recall that the Kronecker delta is just 1 if I equals j, and 0 if I is not equal to j. Just a notation that I'm using to make these statements a bit more compact, where C1 of k is defined as a of k, and then something similar for C2. So with all that said, that's pretty much the end of this video. We can also consider the Feynman propagator. The Feynman propagator, in this case, is just going to be t phi t prime x prime, and then phi conjugate tx. Now, I didn't write out the coefficients like the x and t in front of the size. In front of the phis, but you guys can just write that out yourself for me to make it a bit more clear. So that's pretty much the end of this video. Uh, I hope that you guys enjoyed it, and I hope it made sense. In the next video in the quantum field theory series, we'll be talking about spinor particles, and they have a lot of cool things, a lot of special things concerning them. So, see you all then. Bye.